Hey everyone. I had spent some time recently digging into the Signal app source code for a hobby project that I was working on. So I figured I'd make a pretty casual and hopefully minimally technical video so that it's accessible to as many people as possible about some of the things that I learned about how Signal works under the hood. So for those of you who aren't super familiar with the app, Signal is just a messaging app. It's kind of like iMessage or WhatsApp, except Signal implements by default end-to-end encryption and also doesn't collect your metadata, which isn't the case for any of the other apps like it. So let's get started with a quick intro to how messaging apps communicate over the internet. So we've got Alice on the left here, and we've got Bob on the right, and they want to talk to each other. So Alice types out a message and clicks send, and what happens next is her phone will make a network request, and that'll send her message onto the internet where it'll be routed from servers close to Alice's phone through to servers that end up closer and closer to Bob's phone until the message eventually makes it to Bob's phone. The problem is, Charlie here wants to know what Alice and Bob are saying, but they don't want him to know. So Charlie, he can try to sniff the network traffic, but the problem for him is that the packets are going to be encrypted with TLS, transport layer security, so he's not going to have any luck with that. However, the message isn't going to be encrypted the whole time it's in transit, because when the message gets to the server here, the server is going to have to decrypt it so that it can read what the recipient is and know how to pass it on to whatever the next closest server is. So if Charlie has enough resources or connections or what have you, then he could end up compromising one of these intermediate servers here, and then when the server decrypts Alice's message, Charlie's right there to read it in plain text. So that's not good for Alice or Bob. And this is the sort of problem that led to the idea of end-to-end encryption, which basically means that nobody, not even the intermediate servers, will be able to read the contents of the message along its route. And so that's where Signal, and particularly the Signal protocol, come into play. So here's a diagram of what the first step of a Signal message session would look like. This diagram is actually pretty simplistic, and I'm going to gloss over a bunch of the math, but I'll share links below for those who want to look into it further. So we're here with Alice again, and she wants to talk to Bob, and conveniently they both use Signal. So when someone downloads and registers with Signal, the app is going to generate several pairs of keys, where each pair has one private key and one public key. And so this is the idea of public key cryptography. After that happens, a few of the public keys will be bundled together. So here, like for example, we'll say that Bob has already registered with Signal, and so he's got his pre-key bundle. And that's going to be uploaded to a Signal server, or perhaps distributed across many Signal servers. And in this case, these Signal servers are KDCs, so key distribution centers. And the point of a KDC is to help clients begin a session with a new chat partner. So here, Alice knows Bob is on Signal, so she sends a request over to the KDC and says, hey, I want to talk to Bob. And the KDC responds by sending Alice Bob's pre-key bundle, sends it over here. So now that Alice has Bob's pre-key bundle, let's pause for a moment to think about what she's got to do. So the idea is that Alice and Bob want to communicate with each other, and they want to be sure that they're the only ones that can read each other's messages, and that nobody else can. And so for that to happen, they'll need to agree on a secret that only the two of them know, and they can use that to encrypt and decrypt messages. But maybe they actually haven't met before, so they haven't had a chance to meet in person when they know no one else is around and come up with these secret keys. So they'll have to figure out what sort of shared secret they want to use over the public internet when someone like Charlie could be listening to their conversations. And so that's a pretty difficult situation to come up with a shared secret if Charlie's listening, but luckily there's a technique called the Diffie-Hellman key exchange. And so I'll link to a video explaining it below actually. It's pretty interesting, but in short, the idea is that it's a quick procedure that allows two parties to come up with a shared secret known only between them, even while a third party is observing. So that's what the DH over here stands for, is Diffie-Hellman. And it's an operation that takes in two arguments and outputs a shared secret. And so you can notice that there are three Diffie-Hellmans that Alice performs with a combination of some of her own private keys and some of Bob's public keys that she got from the KDC. And so this is actually the part of the signal protocol that's known as the extended triple Diffie-Hellman, because there are three of them, although actually there could be more. And so one thing that I'll mention, which may not be immediately obvious, is that the output of a Diffie-Hellman is really just a long string of bits. So Alice takes all of these bits, DH1, DH2, DH3, and just concatenates them together and passes them into a KDF, a key derivation function, which outputs their shared secret. And so now Alice has a shared secret, and she could use that to communicate with Bob. She can send an initial message, encrypt it with, she can derive a key from the shared secret, use that to encrypt the message, and then send it over to Bob. And in this message, she'll also include her own version of a public pre-key bundle, kind of like what Bob had put in the KDC, because Bob doesn't know that Alice is the person sending him the message. So Alice will include that, send the message over to Bob, like what happens here, and then Bob will get the message. He'll extract the public keys, because that won't be encrypted. Alice will want Bob to know it. So Bob will take that out, use that to calculate his own Diffie-Hellman. So he'll do three Diffie-Hellmans, the same exact procedure that Alice did, and then get out a shared secret. And now they've got the same shared secret number. And it's really cool because they're dealing with huge numbers. And so the probability that anybody that's not Alice or Bob arrives at the same number as theirs, at the same shared secret rather, is effectively zero. So this is great. Alice and Bob, they can encrypt and decrypt messages and send them to each other. So what's the problem? And the problem is what happens if one of the keys get compromised. And so that's actually something that Signal thought about in the protocol, and they handle this case with what's called the double ratchet algorithm. And the idea is, how can you make it so that if one key is compromised, an attacker can read that message, but no previous messages and no future messages, and can't crack future or past messages with any more ease than the initial message? And the answer is, well, you can just use a different pseudo-random key to encrypt every single message. So you'll get a different key for every single message. So let's think about how that would work. So we jump back here to Alice, and at the point that Alice has now calculated her shared secret, instead of just using it to come up with a message that she encrypts and sends to Bob, what she's going to do is set up some KDF chains, key derivation function chains. So she'll start with the root, use her shared secret to initialize it, and then pass in her private ephemeral key to get out a first value. And so the idea of what a KDF chain is, really quickly, is it's kind of like a crank. You crank it once, and it'll give you a different output every single time. So each crank gives you a different output. So she'll crank this root once, and it'll give an input to the sending KDF chain. And so that's really all that she needs right now. Is she's got the sending KDF chain. Now she'll turn that once and it'll output a key. She'll use that sending key to encrypt the message that she wants to send, and then she'll put the public version of her private ephemeral key in the header, as well as her identity, and now she can send the message over to Bob. So Bob will get the message, he'll do the Diffie-Hellmans just like she did, come up with the shared secret, use his own private ephemeral key, and initialize his root chain. But Bob is receiving instead of sending. So he'll actually here initialize his receiving chain with the output of the root chain. And so he'll give the receiving chain one crank, and that'll output a key that he can use to decrypt the message that Alice sent. And so you'll notice that there's sort of a one-to-one, that the sending chain outputs a key to encrypt the message, and then the receiving chain outputs a key to decrypt the message. And so this is basically it. This is what the first step of a signal session looks like. And so, of course, now Bob, what he'll want to do is send a message back to Alice. And so he would do this by initializing his own sending chain. And so what he would do for that is generate a new pair of ephemeral keys, use the private key and his SS, shared secret, to generate a new sending chain, and then he'll use the public ephemeral key to send in the header. He's doing exactly what Alice did over here. And then now he can just send that message over to Alice, and then Alice will get the message, and she'll be like, okay, I have to receive a message, and go through the same exact steps that Bob did when he initialized his receiving chain. And then at this point, Alice and Bob, they'll both have sending chains, and they'll both have receiving chains. And yeah, so you can kind of imagine it like they're kind of ping-ponging with each other. And this is actually where the double ratchet name comes from. So you'll have the ping pong going on as whenever Alice sends a message, she's going to include her public ephemeral key. This is something that I forgot to mention actually. So they're going to regenerate these ephemeral keys between every single message. And that way the chain will put out a number that's not related to the previous number that it put out in any way. Makes it very difficult to crack. And so in the sent message, Alice will have the new public key in the header, as well as her encrypted message, send it over to Bob, and then Bob will take that public header, or take the public ephemeral key from the header, use it in his receiving chain, or use it, well, actually what he'll do is a Diffie-Hellman to get the new key value for his receiving chain, and then that'll output the value that he'll use to decrypt the message. And so it'll keep going back and forth like that. So that's actually one racket, is the ping pong idea. And then the other ratchet is the Diffie-Hellman ratchet. And so as I was just explaining, with every message that's sent, there's a new key. And then once the recipient gets this new ephemeral key, they're going to have to do one more Diffie-Hellman to get the secret that they're going to use to initialize the receiving chain. So those are the two ratchets, and that's why it's called the double ratchet. And that's basically it. This is what allows Signal to guarantee not just is our current message secure, but all future messages are secure and all previous messages are secure, even if one of the keys is compromised. Because one key being compromised doesn't make future keys compromised, and it doesn't make previous keys compromised. So I just gave a pretty high-level overview of some of the components of the Signal protocol. But if you want to understand it in depth, you can actually just come to the Signal website. I just Googled Signal documentation, and here I can see the docs for all the components of their protocol. So these are the two that we focused on. We talked about the extended triple Diffie-Hellman, and we also talked about the double ratchet. And I totally recommend reading these documents. They go into much more depth than I did. I'll just quickly open the double ratchet because I didn't do a great job of explaining the importance of a KDF chain, but here they do. One more thing that I'll touch on here is, so not just can you read the docs, but they also reference their software implementations of this protocol. So we can just go check them out on GitHub, which is pretty cool. And actually, so this is how I got into it, is I have an iPhone. So I began just going through this Signal iOS, and that's actually something that we can do together. So I'll just clone this down. And we can take a look at it, just step through some of the code and see what's up when we run it. Cool, so it took a few minutes, but now the source code's been pulled down to my local machine. And I was thinking we could just take a look through some of the code and see what it does. And so we talked before about like what's actually happening under the hood with the Signal protocol. And it would be pretty cool to kind of just verify that the things that are supposed to be happening are actually happening when we step through the code. So I've spent a bit of time getting acquainted with this code base, but when I got started, the way I did it was I just downloaded the code and set a bunch of breakpoints. I had been, reading around the files, searching for terms like login or onboarding or things like that, and setting breakpoints where it seemed kind of appropriate, and then just running the program, waiting till a breakpoint got hit, and then stepping through and trying to get a sense for the flow. So I think this time it would be kind of cool to just go through the new account flow. We'll make a new account, and then based on the Signal protocol, we would expect the app to generate pre-key bundles and then register these pre-key bundles with the key distribution center. So let's just run the app and have a look at what happens. Okay, so almost right away we hit this breakpoint in the handle activation. This is before the app is actually finished launching, and it says always check pre-keys after app launches and sometimes check on app activation. So the app actually hasn't finished launching, it seems, so I think that this is checking on app activation because this is the first time that we're running the app on this virtual machine. And we can just have a look in there and see what this method does. But here we can see, don't rotate or clean up pre-keys until all incoming messages have been drained, decrypted, and processed. That makes sense. As we talked about before, when the pre-keys change, then the shared secret needs to be recalculated. And once you make a new shared secret, then you're going to have different encryption or decryption keys for a particular message. And you don't want to get rid of those until you know that there are no more messages left to be processed. So let's continue. Keep going here. Okay. Here's the number that I'll be using to test. Oh, but now that we've launched, we've hit this check pre-keys if necessary again. Keep going from there and see if anything else happens. Okay, so parse and try to register. It's dealing with our phone number text. Okay, I think I've already hit enter on that, so we can keep going. And I'll just check this code. So 1944430. Okay, now that we've got this verification code that we see in the code, 1944430, that looks about right. We're registering for text secure. So text secure actually was the previous name of Signal, so that's what that refers to. We just take a peek and see what this is doing under the hood. So it'll get some auth tokens, deal with our phone number and verification code, and then it'll go down and verify our account and do a bit more. So let's let it keep running, and it just hits this breakpoint here. Let's keep registering. Continue on from there. Oh, interesting. So this looks pretty familiar, doesn't it? Where'd it go? TS Prekey Manager, create prekeys. So this seems promising. So this looks like it's going to be a remote call. I wonder if we can get any more info in here. Okay, so it's going to start an asynchronous operation for this new create prekeys operation. Okay, oh, so I've got another breakpoint here that we might hit in a bit. Oh, right there. So I wonder, is our identity key pair nil right now? Let's step over. And it is, because this is a brand new instance of the app, so let's generate a new identity key. How does that work? I mean, this might take quite a bit of stepping through because there's a lot of code in here. So I'll just press continue. Oh, now this is pretty cool. So we're generating a key pair. We've passed generate random bytes, mentions the curve 255119 Donna, elliptic curve. And then here's our breakpoint. So it looks like some function where we've got a public key and a private key going in. And we can step in there and see what's going on. Oh, so this is actually pretty cool. So this is a C function, or sorry, a C file, and they're dealing with our bits at the bit level. This is pretty cool. So they've got pointers coming in. They're doing these operations, like some bit concatenation. And they've got all sorts of stuff going on up here, actually, in this file. See some mem copy. I actually don't even know what a lot of this stuff is. This is totally new to me. But yeah, it looks like there's a lot of math going on in here. Breakpoint now so that we can get past it. Cool. So that seems to have worked. It wants me to create a pin, so let's do that. So yeah, we were able to see it take in our phone number, go through the onboarding process, and then even create the prekeys, getting public and private keys generated from the elliptic curve that's specified in the documentation. So I think that's pretty cool that we can just step through the code, have a look at what's going on, and for those of you interested in continuing to look a bit deeper, you can totally do that.